We've talked a lot about functions and their derivatives. And I've put a familiar one up here. This is the cart moving at constant velocity across the tabletop. So at this point, I hope you're pretty comfortable that it was linear, constant velocity. We took its derivative, and we got a horizontal line for our graph of velocity. There's got to be a relationship between these two. And we know that this represents the slope of the other graph at every point in time. So you know really well how to go from this graph to make this one, or from this function to make that one. But the other question is there any way to go the other way? Could we go from this graph back here? We go from this function back here. So to help you understand how we go backwards, in other words, the derivative got us from position by getting the slope of this function at all times and plotting it, we got a velocity graph. We're going to try to figure out how to go backwards, and we're going to use the data from that cart moving at constant speed. So it's important to realize that the original function had a unit of meters compared to time, and the new function has a unit of meters per second compared to time. So what we're going to try to do is combine the two units on the velocity graph to see if we could figure out a way back to position. So let's take a look at how we represent the velocity and time on our VT graph. As we said, along the y-axis we're plotting meters per second. So on the curve here, I've drawn a line from 0 up to the curve. And that's a measure of how many meters per second we were going at this time. And notice, since this height isn't changing, that's the meters per second all the way up to this little time period here. In addition, when we walk along this axis, we're talking about seconds. That's what the pink line represents. And the cool thing is, the green line and the pink line, you multiply them together, you get this area I have here. And the units on that area are meters per second times seconds, and that's meters. And it turns out what that area physically represents is the meters that during that time period, the length of the pink line, the cart actually traveled. So it's a way of getting position information from velocity. In other words, going backwards, doing the opposite of the derivative. We go from this function back here. And what I hope is obvious when you look at this is that's a little trickier, because we lost some information. Do you see what's missing from this graph and this function that's present in the other one? Our y-intercept, our original position. There's actually a whole lot of possible graphs that match this guy. Because all we know when we look at this graph is that the velocity was always 0.472. But what are some other graphs that would be true for? Well, for starters, that one. Same slope, different intercept. Or, of course, this one. So going backwards, we have to know some other information. We actually have to know where we started. Here's a graphical way of looking at what I just said. Let's suppose that this is our position function. You can see that we have an original position, an original velocity, and an acceleration. If we wanted to find the velocity function of that, of course we would take the derivative. But all the information about our original position is lost. If we wanted to find the acceleration, all the information about original velocity is lost. And all we're left with is that the acceleration is minus 9.8. So this could be any falling object. And it was important to see that, but what if we wanted to recreate the position function? We can't really go back. Because if we were to go back, how would we know our original velocity? Or how would we know our original position? And the answer is that somebody has to tell you. And you have to add that in to whatever function you're coming up with. This acceleration function could have all of these velocities. And we just have to add our original velocity in when we try to go backwards. And that has to come from some information you're given. So the next thing we're going to talk about is the opposite of a derivative, which is something called an integral. And what you do with an integral is you actually end up taking areas under the curve. We're going to see that if I'm, say, talking from 0 to 1 second, and I was to take my velocity time graph and get an area between the graph and the y-axis, if I get that area, so how do I account for the fact that there was all these different possible graphs? Well, I have to know just what my original position was. So if we look at this function, we could call this whole thing here delta x. And what that means is that our new position is our original position plus delta x. I found this area here, delta x. It doesn't uniquely give me any one of these points unless I know what my original position was. So if I add my original minus 0.242 to delta x on that graph, I'll get where I am now. And I can keep going. If I then go to 2 seconds, so I'm including all the original area as well. And then I add, or where it was at the beginning, to the area under the curve out to 2 seconds, I'll get this. And it will actually regenerate the graph. So let's try that with our data for the constant velocity cart. Again, there's no way to know from the velocity graph what the starting position was. Because I wanted to show that this velocity graph can regenerate the position graph very well, I actually looked at the position graph and found what the value was for my first position, and it was 0.403. So I then went to my velocity graph. I drew a rectangle representing that constant velocity of 0.472 for a certain amount of time. And the area of that rectangle, I then added length times width to my original value, and I got 0.592. When I plotted that on the original graph, I got something really close to what the original position graph said. The motion continued, however, so during this next time interval, which is brown, the area under the curve is represented by this box. I added that area to the 0.592 I had before, and I got a value of 0.781, which, if you look, is right about here. So you keep adding the area in each time interval to whatever you had before, and that's what gives you your new position. And if you do that repeatedly, with just that one piece of information, where did you start? This graph can tell you what the position graph looks like. You really can go backwards. So I want to make sure we understand where our constant velocity equations v equals at plus vo and y equals 1/2 at squared plus vot plus yo, where they actually come from. So the constant velocity equations basically come from this graph, a versus t, and a constant 9.8 is the acceleration on it. If, let's say, we take the area under the curve from 0 to 1 second, which I'll highlight here in purple, so it's like this area here. Let's say our original velocity was 0. If we were to plot that velocity on a vt axis, we would get 1 second times 9.8, or about 9.8, this purple dot. If we then go get a different area, we'll say the area from 0 to 2 seconds. Notice I'm including the purple area. If I add that area to my initial velocity, VO, I would get 19.6 as my velocity. And that's what I'm doing here. I'm successfully taking larger and larger areas, and I'm plotting them on the VT axes. So again, if VO is 0, then we're going to get 39.2 for that area, and that's out here. So the equation V equals AT plus VO literally comes from the AT equation, and by getting the areas under the curve of progressively larger and larger areas. Now, the same thing happens to go from V equals AT plus VO up to the more complicated equation. If you progressively get these areas, so this one is of course a triangle, this area here, and if XO was 0, this green area would correspond to this point, and we can keep the process going. Up to 2, we'd have a larger triangle. And that would be this area. And we could keep plotting, and we would actually see the parabola that we know to be true from the equation y equals 1/2 at squared plus vot plus yo. So we can even do that without calculus, because the areas under the acceleration graph are just rectangles, length times width. The areas under the velocity graph are just triangles, 1/2 base times height. We don't really need a lot of calculus to get the areas under those curves. But what if I had to take the integral again here? What would be the area under this curve? That would be tricky to do. And although the integral of position isn't going to have any meaning for us, there may be a velocity function we run into at some point that is parabolic or some other curve. So how do we take that velocity function and get the area under it? That was one of the tricks that had to be developed using calculus.
How did you get the area under this curve, which is what you would have to do to get a position function? Well, one trick you could use is you could take little slices. So imagine that that yellow line is a rectangle. The area would be length times width. And since the width is so small, it doesn't matter that there's an upward slope here. In that tiny little period, it's basically flat, in that tiny little space. So what would it be? Well, its area would be, its length would be delta t, and its height would be v of t. In other words, whatever this function is. So we would add up all of these little numbers for all these little slices that we could take. We could take another infinitely thin slice there, and another one here, and another one here. We basically would be adding up so we'd be summing these. We would have delta t1 times v of t plus delta t2 times v of t, etc. So that would get us eventually the area under here if we added up all of these different stripes. What would we write? We could just write that as x is the sum of all the delta t's, I'll say delta ti, times the velocity function during that time frame. And we would say we'd go from I equals 1 up to the number of slices we have. Well, we can abbreviate that with this new idea, which is called the integral. We replace the sum symbol with the integral symbol, and we write v, and then we write dt. So we still have the v from before, and then that delta t, when it got infinitely thin, just became dt. So this integral just symbolizes the sum of all of these slices. How do we do it? Well, in math class, you will derive all sorts of formulas to go from a function to the integral of that function. But for a polynomial, it's pretty easy. If you have a function ct to the n, its integral with respect to time, you just up the power by 1, and then you divide by the new power. You do have to remember to add the constant of integration because we don't know what the original value of the function was. So what would it be for this case? We'll do it out. If v was 17t squared, then x will be the integral of 17t squared with respect to time. And that will be 17t to the 2 plus 1 over 2 plus 1 plus whatever our original position was. So if you're ever given any of the functions, position, velocity, or acceleration, you could typically generate the others as long as you're given some sort of initial conditions. So here's a question that I think is useful to solve. I give a non-linear velocity function here. I want to know where it is. I want to know what's its acceleration. So the where it is, the position, we basically just take the integral of that velocity function, which ends up being this. And notice we just have a constant do for original distance. Well, we have to be given that. And notice the problem did. So we just put the 18 in for that. It asks where it is at t equals 5 seconds, so we just plug 5 in for time, and we end up with our answer. So from velocity to position is taking the integral. If it wants to go from velocity to acceleration, we just take the derivative. And again, we plug in our 5 for time. We get our answer there. So you should be comfortable going back and forth between all of these functions.
If you're going in this direction, you're integrating. If you're going in this direction, you're taking the derivative.